everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to be covering the law of large numbers, the theorem that tells us when a sample average actually starts to converge to the truth, and how much data you really need before historical averages can mean anything. We're following Danny, a gambler with a mountain of debt, working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to his family fortune. Today he pulls out a letter where the rational quant challenges a claim Victor made about his own investment track record. He opens up another one of those mysterious letters. The first thing to establish is what the law of large numbers actually says. Suppose you have a random variable, something with a true expected value and a true mean mu. You don't know what that mean is, so you start collecting observations, you compute the sample average, and the question is, as you collect more and more data, does that sample average get closer to the true mean? The law of large numbers says yes. More precisely, if x1, x2, all the way up to xn are independent and identically distributed random variables, all drawn from the same distribution, all independent of each other, with mean mu and finite variance of sigma squared, then the sample mean converges to mu as n gets larger. More formally, this essentially says that as our number of observations goes to infinity, we end up zeroing in on the true mean with our sample mean. Specifically, if we were to pick any fixed distance from the true mean, no matter how small, then the probability that our sample mean would end up outside of that distance from the true mean would end up converging to zero as n ends up going towards infinity. So no matter how small you make that distance, you can always find a large enough n to push the probability that you miss by that amount below that, and even push it down all the way to zero. That's the theorem. The intuition behind it is just as important. When you average independent random variables, high draws cancel out low draws. The noise gets diluted as the sample grows. And what's left is the signal, the true underlying mean. It's not that the individual observations become less random, each one is still drawn from the same distribution. It's that the average of many random observations ends up being far less random than any individual one. Now, how quickly does convergence happen? That's a practical question. The standard error of a sample mean is sigma divided by the square root of n, the number of observations. That's the typical distance between your sample mean and the true mean. As n gets larger, the denominator grows, and the standard error shrinks. The convergence is real, but it's slow. It scales with the square root of n, not with n itself. To cut your standard error in half, you need 4 times as much data. Here's why that matters in practice. Suppose a fund manager claims 5 months of outperformance as evidence of his skill. His average daily return over that period was positive, so he concludes that his true return is positive, that the run was driven by genuine edge and not luck. Let's put numbers to it. Take a stock with a true expected daily return of 0.04% and a daily volatility of 1.5%. 5 months of trading is roughly 105 trading days. The standard error of the sample mean is 1.5% divided by the square root of 105, which ends up being about 0.146% per day. Since we're working with a normal variable, we know that the empirical rule says that the sample mean will land within about 2 standard errors of the true mean roughly 95% of the time. So somewhere between roughly negative 0.25% and positive 0.33%. Think carefully about what that interval contains. A manager whose true alpha is 0 could produce an average daily return anywhere in that range. A manager whose true alpha is slightly negative could produce positive sample returns over 5 months. A manager with genuine positive alpha could produce negative sample returns, and 5 months of data is too noisy to tell those cases apart. The law of large numbers guarantees the average converges, but the convergence at 105 observations is still nowhere near tight enough to distinguish skill from luck. How much data would you actually need, though? Well, with 500 trading days, or about 2 years, the standard error drops to 0.067%. The sample mean still lands within about 0.13% of the true mean only 95% of the time. Arguably not enough. With 2,500 trading days, roughly 10 years of data, the standard error drops to 0.03%. Now the sample mean is concentrated within about 0.06% of the true value the vast majority of the time. That's tight enough to actually start making meaningful decisions. 10 years of clean, consistent data is giving you something real, while 5 months is not. So the law of large numbers guarantees convergence, but in finance with high volatility assets and small expected returns, convergence can require far more data than people intuitively assume. The expected return is small relative to the noise. The signal-to-noise ratio is low, and that means the law of large numbers takes a long time to do its job. There's also an important condition embedded in the theorem. Independence. The law of large numbers requires that observations are independent. So each new observation tells you something new and is not just a replay of the last observation. In finance, that assumption deserves scrutiny. Daily returns can exhibit serial correlation, where periods of high volatility tend to cluster. So yesterday's return has some predictive content for today's variance. A company's underlying risk profile can shift fundamentally over time. As executives and board members shuffle in and out of a company, and as the competitive landscape changes, things can become fundamentally different than they were in the past. When independence fails, convergence to the true mean can be slower, or require modifications to the basic theorem. The law of large numbers doesn't disappear, but it requires more care about which observations are genuinely informative. The law of large numbers has a direct and important application in portfolio construction. If you hold in stocks, each with an expected return mu and variance sigma squared, an equally weighted portfolio ends up with a variance equal to sigma squared divided by n. As n grows, that variance goes to zero. The idiosyncratic, firm-specific noise gets averaged away. The law of large numbers is the mathematical foundation for why diversification here is going to work. What remains after diversification is systematic risk, the common component that can't be averaged away because it's correlated across all holdings. That's the floor. But below that floor, the law of large numbers is doing exactly what the theorem says it does. You hold more independent positions, so you average out more of the noise. Now there's a second application that comes directly out of the law of large numbers, and it's one of the most powerful computational tools in quantitative finance, the Monte Carlo simulation. The core idea is simple. Suppose you want to estimate the expected value of some function of a random variable. This random variable could be anything. It could be the expected payoff of a complex derivative, the probability of a portfolio losing more than a fixed amount, the expected pension liability under different interest rate scenarios, anything like that. Many of these quantities don't have clean, closed-form solutions, and the law of large numbers tells you exactly how to handle that. When we run a Monte Carlo simulation, we draw in random samples from the underlying distribution. Then we use those values to compute the outcome among each of those samples. Finally, we average across all the results. By the law of large numbers, that sample average converges to the true expected value as in the number of observations grows. Consider a European call option. At maturity, the payoff is the maximum of the price minus K, or zero, where the price is the stock price at expiration and K is the strike. If the stock follows a log normal process, you simulate thousands of paths for the price, compute the payoff for each path, discount back to today at the risk-free rate and average. The Monte Carlo estimate converges to the true option price. With enough simulations, you can get as close to the true price as you want. The accuracy improves at a rate 1 over the square root of n, the same square root scaling we saw earlier with the standard error. To cut the estimation error in half, you need 4 times as many simulations. That's slow. For a simple option with a known analytical formula, you wouldn't bother. But for path-dependent derivatives, multi-asset portfolios, or any problem where the underlying structure is too complex for a closed form, we need to turn to the Monte Carlo simulation and take advantage of the law of large numbers to get an estimate of what our mean should be. Danny puts down the letter. He notices the date at the top. It's the oldest letter in the entire box, and the rational quant is questioning Victor's analytical reasoning and his skill as a fund manager. Victor believed that his 5 months of outperformance was strong evidence of his skill as a fund manager, but the rational quant was challenging this idea by showing him the law of large numbers. There was not enough data to know what Victor's true skill was, and the rational quant was calling him on it. Danny had been calculating his own track record the same way Victor apparently had. He's had stretches, good runs at the table, sessions where he ended up well ahead, where the results felt like confirmation that something of his skill was real. But a couple good runs in a row isn't enough of a sample size to make any strong inferences. So that's the law of large numbers. Sample averages converge to the true population mean as the sample size grows. But convergence scales with the square root of n, and in finance, where expected returns are small relative to volatility, that ends up requiring far more data than most people assume. Monte Carlo simulation is the direct computational application. Simulate, compute average, and the law of large numbers guarantees the estimate converges. Both applications rest on independence, which is an assumption worth checking carefully anytime you're working with financial time series data.